A single tornado can kill hundreds, injure thousands, and cause billions of dollars in damage in just hours. Thus, it is critical that tornadoes are forecasted accurately for citizens and municipalities to adequately prepare. The GOES-R series satellites are an essential tool for this, with better data collection technology than the previous generations. By analyzing GOES-16 ABI imagery leading up to a tornadic severe weather event on April 23, 2021, we attempted to answer the following question: how far in advance can features affecting tornado genesis be detected using the GOES-R ABI? Ultimately, few tornadoes were produced that day, and fortunately, no one was injured. However, our research will provide useful information to anyone trying to forecast future tornadoes with satellite observations, potentially saving lives by giving people more lead time for tornado threats.
The low-pressure system responsible for the event was evident on the 6.95 micrometer mid-level water vapor band by 20 UTC on April 19th, 4 days before the event. Water vapor imagery is useful for identifying low-pressure systems because it reveals where air is being lifted. Just after sunrise on April 23rd, over 7 hours before the first tornado report of the day, a large region of low-level stratus was visible on the 1.61 micrometer snow and ice band. This band was used because it differentiates between low-level and upper-level clouds. The extensive stratus indicated substantial surface moisture, an essential thunderstorm ingredient. On the 0.64 micrometer red band, cumulus development became apparent along a dry line by 1820 UTC. The red band was used because its half-kilometer spatial resolution, sharper than any other band, makes it helpful in detecting mesoscale or microscale features. Around the same time, an area of cool surface air could be seen in the southeastern Texas Panhandle, evidenced by gravity waves and broken stratus instead of the bubbling cumulus in the warm sector to the south. Cold surface temperatures make surface-based storm development less likely, and sure enough, the main storms developed to the south of this region.
Surface analysis from the Weather Prediction Center confirms these satellite observations, showing low pressure in the Texas Panhandle, a dry line across western Texas, and relatively cool temperatures in southwestern Oklahoma. At 1900 UTC, the first storm anvil was evident on the 1.38 micrometer cirrus band. Anvil clouds form when a cumulus updraft hits the top of the troposphere and its water droplets change to ice, which is clearly visible on the cirrus band. Once storms were underway, the 11.2 micrometer long-wave infrared band was used to monitor them. This specific band was used because cloud top temperature is a good proxy for storm intensity as it is strongly correlated with cloud top height. It showed that of the three supercells in the warm sector, the northernmost one was most intense. This was clearly apparent by 21:20 UTC, over an hour before the first tornado touched down. The two storms further south did not produce any tornadoes. Thanks to the high spatial resolution of the red band, a couple of these storms could be seen visibly rotating. However, observing rotation from satellite is only possible in a small portion of supercell cases because the anvil usually obscures the updraft.
Here is a table of specific results showing the lead time for each feature. The lead time is defined as the time between when the feature was first observed and when the tornado was first observed. The surface cold pool was the most unexpected of the features, resulting in the tornado threat being significantly further south than originally predicted. The earliest feature detected was the trough, which was observed 4 days in advance of the tornado. The latest feature detected was supercell rotation, which was only found 30 minutes in advance. But this feature is unreliable, meaning you usually won't see it before a tornado. So it's not great for forecasters to depend on this. The latest reliable feature detected was storm maturity, which we found 1.2 hours in advance. Generally, the larger the features were, the earlier they were detected, which leads to the conclusion that larger features tend to be more persistent. However, they also give us less information about the specific location geographically of the tornado. Confidently predicting a specific threat area was only possible about 2 hours in advance when the smaller features began to prominently emerge. Our results can be used as a guide for forecasters so that they can know when to expect each feature to appear. However, studying more cases would allow the information to be more generalized. We would like to acknowledge our mentor Eric Lodal in guiding us through this project. We also thank NOAA for providing high quality satellite data for public use.